Hello and welcome back to the basics of calculus. So in the last video, we talked kind of about the idea of a photo versus a video. So just to kind of briefly review that, we talked about the idea of taking pictures at instantaneous moments versus the idea of taking videos over time. We used that to introduce the concept of a limit. So let me finish writing this really quick. Taking pictures versus videos. We use that to introduce the idea of a limit. And remember, the limit was this idea of showing how something behaved as we approached a specific point. So for example, we talked about behavior around a given point. So what we did here is we kind of used pictures or snapshots as a stepping stone to create videos. And in fact, this is exactly how this is done in the real world. When you see a video camera, what it's really doing is it's taking a series of instantaneous shots, one shot to the next, taking a single picture at a time, and then it's playing those back at a given rate. And that's actually where the idea of frame rate comes from, and there are a lot of interesting things you can do with videos because of that, but we'll go into more detail about that later maybe. But we use this idea of the limit to kind of introduce the idea of videos in math, this idea of continuity. So in this video, what we're going to be talking about is we're mainly going to be talking about a more formal definition of what we would call discrete math, and then what we would call continuous math. Discrete versus continuous math. So discrete math is very old. It's a very old kind of math that dates all the way back to really the first time that humans ever tried to do math. Discrete math is a way of handling things in what are called discrete chunks or in indivisible chunks. So for example, the ancient Egyptians, when they first developed their own kind of math, or the ancient Babylonians, they created the natural numbers. We know the natural numbers to be the whole numbers, the whole positive numbers that we use to count. So natural numbers would be 1, 2, 3, 4, 5, and so on. Now, this was useful for them. They could say, well, I have one goat, and then I add another goat. That's going to give me 2 goats. And so this is an idea of discrete math. This is the primary example of discrete math, where what I have is I have discrete parts, so 1 goat plus another goat equals 2 goats. I have distinct parts of something, and then I describe a relationship between those things. So this is discrete math. So this evolved, of course. We evolved the idea of repetitive addition into multiplication. You know, if we have 1 plus 1 plus 1 plus 1 4 times, that's the same thing as just 4 times 1, which we know is equal to 4. Then, of course, we did the same thing with subtraction, of course, iteratively subtracting something. That gives you the idea of division. And from there, we developed other operations. And all of the operations we have are based off applying these ideas of addition and subtraction to higher and higher levels. And they were all originally used, and the key here, all originally used to describe discrete math. They were all used with these discrete numbers. And that's very important. All of these come from the idea of a discrete number. When we talk about continuous math was introduced a little bit before Newton. It was talked about a little bit before him when people started talking about functions. And so functions were a brand new way of describing relationships. Traditionally, in purely discrete mathematics, when we described something, we had to describe the relationship using certain numbers. There had to be some number here plus some number here, both of which had to be known, and that would equal some other number. This can be thought of as our snapshot. This is like our picture, so kind of a reminder, like the picture. At a point in time, it's like a snapshot of a specific number at a specific point in time. So like number 1, 1, plus number 2, 3, plus number 4, 4. And kind of shows weird numbers for that, but So that kind of combination is like a picture. So then when people started coming up with the idea of using function notation, this was a way to generically describe some relationship for any choice of number. So this got into the idea of function notation, or really just functions in general, where we could generically describe some relationship for any number. And what that did was, let me write that down really quick, because it's really important too. Generic way of describing a relationship. And what this was done with variables. We used variables like x and y to describe these things. What we would say is if we had some input x plus some other number, 3, a constant number, that would equal some output number, y. And depending, so we call this the independent variable, depending upon this variable, depending upon the choice of x, so depending upon the choice of x, we would get a different y. So y changes based on x. We could say y is dependent upon x. We choose x, that then gives us a y. And that's the whole point of a function, that y, some number, is a function of x, meaning that it's equal to some relationship that involves x. So it's equal to some relationship, so 3 plus x. And we needed a way to generically describe that, and that's where function notation comes in. The idea that y is really just equal to a function of x, or as we write, f of x. And so that's really important because these ideas of functions now move math from discrete ideas using specific numbers to continuous ideas, where we can change some variable, we can change a variable, and we can see how that changes the output. We can see the way that it affects this y. So see the change in output. Now, until Newton and until the invention of calculus, this was really just used as a way to solve for unknowns. For example, we would have situations where maybe you didn't know, you had 5 cows, right? And 3 of them were female, and then you didn't know how many were male. So we would plug in some variable here and we'd say that 5 is a function of x, but really we just want to solve for x. In terms of that, we would subtract 3, of course, you'd get that x equals 2. You have 2 male cows. But this right here wasn't really an idea of functions, and the idea of pure functions, of things that had different outputs depending upon the input, really came about with Newton and his contemporaries. So this wasn't a function. And that's a key point there in the evolution. Functions really came about with Newton when we started talking about y equals f of x. Now the problem was that these functions, these relationships, there was a way to describe the relationship, but there were really no good ways to describe the behavior. And what do I mean by that? We talked about this in the last video. There were no ways to talk about how it increased, or how it decreased, or the maximum of the function, the minimum value of the function. There were ways that we could numerically find it. We could plug in points, but we needed ways to analyze the entire function. So I should correct that. I should say no analytical ways. Whenever I say analytical, all that's saying is that there was no way to just generically find these kinds of things about the function. So what had to happen is we had to introduce the idea of the limit. This is where the limit comes in. The limit provides a way to analyze the behavior of functions, provides analytical way to look at behavior. And that's why the limit becomes important. We now have a way, it's really a numerical way too. If you think about it, the limit talks about what happens as you approach a specific number. It has a specific number there, so the limit as something approaches another number, and we're going to see what happens to the function. But the key about the limit is that we can do that at multiple points along the function. And if we can do that at multiple points along the function, we can kind of use that to generate other functions. So by collecting up multiple limits, we can begin to create limit-based functions. And that's the key here. When a function is limit-based, we're really starting to get functions that can show us the behavior of a function. We're starting to get things that can show us how a function behaves. And that's because this limit acts like a video camera. When we collect up enough of those videos around certain snapshots, we start to get an idea of how the function behaves. That's what the limit does. It acts like that translation to the camcorder that we were talking about. And so that's why this transition from discrete to continuous math is all centered around this idea of the limit and the function. So what we're going to be doing kind of from here on out is we're going to be talking about functions. There won't be any discrete math that's going on. Calculus is the study of continuity and the study of functions. So calculus is really defined as the study of change. Study of change. And what that means is it's how some change in input has an effect on an output. And the way we do that is with the limit, because the limit tells us how varying an input around a certain area will affect the output. And that's what calculus is all about. It's all about that study of change, how some change in input has an effect on an output. And that's really why calculus is such a fundamental tool in the real world. In the real world, things are not discrete. Many of the things that we talk about today, many of the more complicated things, do not involve discrete values. For example, if someone is throwing a ball, so they throw a ball through the air, it lands on the ground, boom. Now we know that this ball is going to change velocities. If you don't know that, a way you can prove it to yourself is that if you imagine throwing a ball up in the air, so say instead of doing that, I throw it straight up, it has to come down at some point, right? Well, for it to come down, originally it's going up with a set velocity. I throw it up with some velocity v, comes up, and eventually it goes back down. For that to happen, it has to stop in midair, meaning the velocity has to change. This is called acceleration, and we can talk about that more later on. It's really a concept related to physics, but what we see here is the velocity is changing. So this would be impossible to talk about without the use of calculus. We can't talk about the idea of a changing velocity if we don't have a way to talk about change. And that way to talk about change is really with calculus. The most effective way to talk about change is using calculus and using this idea of a limit. And in fact, everything in calculus you'll see is truly defined in terms of the limit. I would say this is the main pillar, in addition to the series, which we'll get to later on. This is really the main pillar that underlies calculus and makes it so effective, and really such an effective technique for analyzing things. So this is kind of a short video. It's really just to kind of formalize this idea of discrete versus continuous math, so that there's a really good understanding of what we're talking about when we discuss discrete versus continuous math, and so that there's really an understanding of what calculus is used for, why we're studying calculus, what the importance of it is. Really, the importance is so that we can talk about these continuous functions, so that we can talk about change, and so that we can talk about how things vary with respect to a given input. Maybe not just time, maybe it has to do with distance, maybe it has to do with an input of money, things like that. It's how some function changes based on a given input. And that's really what I wanted to stress here, that idea of discrete versus continuous and really what calculus is. So I think that's it for this video. Thank you for watching, and I hope to see you next time.